Hey, what's going on, fellas? In this video we're going to take a look at this ozone electrode that I've built. This is a double-walled electrode that puts off ozone gas on both sides of the electrode. And we're going to discuss the importance of being able to adjust the frequency of your transformer. You have to be able to achieve the resonance frequency of your specific electrode, because this is a capacitive load. The size of the electrode is in direct correlation with the frequency needed to drive it at its maximum output. So let's take a look at what adjusting the frequency does. And I'm going to change the frequency to show you what happens when the frequency is not in resonance with the size of the coil. Anytime you change the size of this coil or add more coils to a specific transformer, you will have to change the frequency. You can see here, I'm going to leave that screwdriver in the frequency adjuster and turn the light back out. Now I'm going to mess with the frequency here. Now watch what happens. See how we lost power there? Let me go all the way the other direction. You can hear it change tone also. For example, right now we're at about 32 watts. Okay, you can't see it with the lights on, but the coil is running. Remember how we were at like 32 watts? We are now at about 85 watts on this particular coil. The power factor is pretty horrible, 0.47, not even 50%. That's the volt amp wattage, about 0.76 amps. So, I don't want to blow this coil up, so I'm not going to turn the voltage or anything up, but essentially what we would want to do is then decrease the voltage to a point where it stops working the best, because adjusting the frequency can give you more power than adjusting the voltage, but high voltage is bad for the dielectric. Eventually you'll burn up the dielectric for no reason. You want to keep the coil as bright as possible. You can tell by the color when you're making good gas. In my opinion, that could be wrong. I have not read that anywhere. Essentially, this is the end cap for the ozone, the pressurized ozone generator. You can use PVC on ozone, but it discolors a little bit. It just turns a yellow color from what I've read. It is okay to use it. It's a B rating, which means it will suffer some slight discoloration, and that should be the only hazard with that. Everything else is going to be stainless steel. But I wanted to show you that one thing about the transformer. And on this particular transformer, this is the frequency adjuster here. All this other stuff, this is the duty cycle, which I have on maximum. This is the voltage over limit control, and I believe this is the voltage, but I don't know. The translation is terrible. This thing can do 1,000 watts, so it could basically do a lot more coils than this. And as I said, I don't want to stress this coil too much, because I don't want the dielectric to break. So there's a limit. You're always trying to find that limit to in between maximum power output and durability. So don't even need to hook the cooling fan up for this particular setup. I believe this is only a 4,000 to 8,000 kilovolt transformer. I think it's 8,000 kilovolts. I got this off AliExpress. The only place you can find stuff this exotic. Let's take one more look at that. Still glowing pretty good there. Big, massive ozone cell. And we're going to be... Okay, we are now out of resonance. And that is back in resonance. Now, resonance is a hard thing to describe to people. Basically, the best analogy is, imagine you're pushing your child in a swing. And if you push the child at the exact proper moment, then the child will begin to swing better. But if you push it the wrong time, they won't swing at all. So that's what resonance is about. It's this is a capacitive load. So this coil is acting like a capacitor. This is a double-walled electrode, which means both sides of this electrode is giving off gas. Okay, so this is what we were looking at. The flow rate that we need on this thing to get it to self-cool itself is a lot higher than what we're pumping through it. It's getting a little bit hotter than I would want to see it. The ozone gas coming out of that hose is so pungent, it'll singe your nose hairs right off your face. I just took a quick little whiff of it, and man, is it some toxic stuff. So we're definitely venting that gas out of the building here. This is the power supply we're working with. Only doing about 90 watts right now. We don't want to blow this cell up during testing. And I want to be sure all the silicone and stuff is perfectly dry before we pressure this thing up. It has to be able to withstand a back pressure of 50 psi's continuously, and that's going to be the next test. I just wanted to see how it heats up with this low of a flow rate. I think I'm going to go ahead and just scratch this out of the test on the next one, and we're just going to pump dry air through it so we can see that it does in fact cool itself. I don't want it getting over 100 degrees, to be honest with you. I would rather it didn't. Okay, so I'm finding that it's best to have this thing on its side for cooling. That's just a piece of black tape we're looking at, so we can get an accurate reading of the temperature. Notice the difference in temperature of the black tape and the tube itself. Now, I had this thing positioned upright initially, and it got very hot towards the top. The flow rate is just too small. This is a 9 liter per minute oxygen concentrator, and we just need to be putting a lot more oxygen through this thing to help it cool itself off. It wasn't made for such a slow flow rate of gas. So I'm just letting this thing run pressure free for a while to see how hot it gets. I do have a fan blowing on it because we are going to want some type of air cooling on this thing. But yeah, there's the power supply. I don't know why that capacitor is getting so hot. We're getting a little too warm for my liking. This really isn't that big a deal, but here's a quick look at the other electrode. But we have to wait till the other transformer gets here. Now this copper will turn black in the ozone, but that's no concern to us. This doesn't have any mechanical feature we need to worry about to it. They say it just discolors, so it should be just fine. Inside of there is the other electrode, and here is where the gas is passed through. And the outer electrode, and this is a high power water cooled outer electrode. You can see there. And this slides inside of that and produces gas both on the inside of this quartz tube and on the outside. So it's actually twice as big as it looks, because most units do not produce ozone gas on the internal corona. It just does its thing and they don't flow gas over it. Okay, Juan, as soon as our pressure testing is done, I'm going to have this thing shipped off. I did have to wait a couple extra days for some silicone to cure. I wanted to make sure it was fully cured, and everything seems to be working out. One thing that I did notice during testing was that the more you increase the pressure, the less current draw from the ozone power supply. So that's not necessarily a good thing. We may have to crank up the power a little bit to compensate for that. I just wanted to warn you of it, that when we pressure up to about 50 psi's, the current draw on my initial setting was reduced by about 50%. So it is substantial. We will want to beef up the current when we increase the pressure, and I will let you know as soon as the 5,000 watt transformer has arrived for the other larger coil system that I showed you. And any subsequent build from this point is going to go a lot faster because I now have a supply chain put together. There will be no more development or testing or any of that, and I'm hoping to have this thing headed your way by Monday.